Hi, my name is Daniel Levidov from the Institute for the Wireless Internet of Things at Northeastern University, and today I'll be talking to you guys about AiEEG. AiEEG is our embedded seizure prediction prototype, which we do using deep neural networks, and it is meant for implantable treatment of epilepsy. So let's start off with an overview of what we'll be talking about here today. So I'll start off by introducing our problem, which, as I've said before, is epilepsy or seizures that are caused by epilepsy. Then we will talk about the challenges in implementing AiEEG. Then we will talk about the approach that we've taken and how we've actually developed AiEEG, the network that we've trained, and kind of the system constraints that we've taken into account. Then I will go over the data set that we've used to train. And then finally, I will show our results, and then I will conclude. So let's start off with our problem. So what is a seizure exactly? A seizure is caused by epilepsy and involves a unique rapid rhythmic firing of neurons in the brain. And depending on the location in the brain, there's different symptoms that can happen, such as, convulsions and uncontrolled movements that cause complete interruption of lifestyle and can be at huge risk of injury for the patient. About 3.4 million people in the US have epilepsy in 2015, and 65 million globally are affected. The risk of premature death is 3 times higher than those without epilepsy, and 30% of patients are actually medically intractable, meaning that drugs actually don't work in treating their epilepsy. So there's clearly a need for other kinds of treatments, such as implantable medical devices, as we will talk about here today. So most implantable medical devices for seizure prediction generally rely on something called a EEG, or Electroencephalogram. And what an EEG does is it records the electrical signals that happen between the neurons in different parts of the brain. The reason this is relevant to seizures is because, as I've said before, the way seizures work is it's through these rapid firings of neurons in the brain. So the neurons communicate with each other through electrical signals, and the EEG measures those electrical signals. The most common, I would say most famous form of EEG that everybody knows is the scalp EEG, as seen in this picture on the bottom left here. And it involves these different electrodes that are placed on the scalp, each measuring the differential electrical activity between two electrodes, represented as a single EEG channel. So if you look at this picture here on the bottom right, which has multiple lines, each horizontal line is a different time series measurement of a pair of electrodes that is seen in the picture on the left. So maybe these two electrodes would correspond to this line right here, and these two would correspond to this line right here. An alternative, however, for implantable medical devices is to use something called an intracranial EEG, or AiEEG. And an AiEEG can be seen here on the right, different types of intracranial EEGs. So you have your grid electrodes, which is this, this grid that's placed right on top of the brain. You have a strip electrode, which is just a thinner form of a grid electrode, and you have these depth electrodes, which are actually injected deep into the brain. But why would one want to use this more invasive form of EEG? Why not just use scalp EEG? Well, because it doesn't have to deal with the skin-skull barrier, intracranial EEG has higher accuracy and higher spatial resolution, and also higher signal-to-noise ratio. And furthermore, it's for patients with more severe forms of epilepsy, which is actually what we're aiming more towards treating with our work. But as we can see, AiEEG isn't wireless. It requires a hole to be drilled outside of the head to have a wire that can interface with the outside world. And we don't want that, right? We want to make the whole process wireless, and we also want to give the electrodes smart capabilities, right? We want them to be able to classify things, understand what they're seeing, and rather than just recording raw data. So how can one actually predict a seizure using intracranial EEGs? Well, let's start off by looking at an EEG, a 3-channel EEG of a seizure actually happening. So there are 4 stages of a seizure. So first there's the seizure itself, which is the ictal state. Then there is the pre-ictal state, which is the moments leading up to a seizure. And generally this varies, the length of this state varies per patient, but is generally seen as an hour before the actual seizure happens, which is what we consider it to be in our paper. Then there is anything an hour or longer before the seizure, which is known as the interictal state, which basically just means there's no seizure happening. This is the non-seizure state. And then there's also the postictal state, which is right after a seizure. So the way most works generally address seizure prediction is they try to distinguish between the interictal state and the preictal state, so the non-seizure state and the pre-seizure state. And the idea is that you have a classifier that takes as input, this time series EEG, and once it reaches a pre-seizure state, it raises an alert and notifies, the proper authorities or the patient itself. And once alerting, there's also other things we can do as well. Specifically for medically intractable patients, there are other treatments that you can perform to help mitigate the effect of the seizure. For example, vagus nerve stimulation and deep brain stimulation are the most common ones, and generally involve stimulating different parts of the body to help reduce the effects of the seizure. For example, vagus nerve stimulation will send pulses to the vagus nerve here in the neck, and deep brain stimulation will quite literally stimulate deep parts of the brain to reduce the effects of the seizure. So now that we understand the problem that we're facing, we can talk about the challenges that we face in developing a working seizure prediction prototype. And one of the most obvious challenges is actually the seizure prediction itself. So how well can you classify the stages leading up to a seizure? The problem here is that one size doesn't always fit all for a classifier. One classifier that works really well for one patient might not work very well for another patient because of predisposed conditions and just the different ways electrodes are placed, a number of reasons. So there needs to be a form of personalization per patient in the classifier itself. Furthermore, once you have a good classifier, you need to take into account the real-time considerations, so the hardware and latency constraints. And this is even more prevalent in our case when the device is implantable because it has to be small, so it can't have large, powerful computers. It'll have really limited resources with limited computational power, energy, and communication capabilities. So it needs to do what it does in a very efficient way, especially the classification part. Furthermore, no paper has taken into account reconfigurability. Most papers that have done classification, even in a form of real-time device, have just developed it and assume that this device can be put inside someone's head, inside someone's brain indefinitely, but that's not really the case. If your device can be reconfigurable and furthermore in a way that avoids excessive surgery, when you can update it, tweak it, change parameters without ever having to take it out, that would be extremely useful to the patient, especially as more improved classifiers and algorithms come out later on in time. And to address these challenges, we can now go over our approach for developing AiEEG. So as we've said before, AiEEG is meant to be an implantable medical device, specifically one that is interfaced with the intracranial EEG. And what the intracranial EEG does is the sensors feed data to the DNN on AiEEG. The DNN then predicts seizures and communicates these predictions through a TX chain, which uses ultrasonic communication to communicate with a gateway outside the human body. The reason we use ultrasonic communication is because this is the only real safe way to communicate effectively in vivo inside the human body with enough power. And there's a paper actually here on the bottom which can talk more about using ultrasonic communication for intra-body applications. In addition to doing deep learning and communication, there's also a memory which will store the weights of the deep neural network and also any kind of buffering and FIFO that needs to be done for the EEG data, and also a processor which will handle the movement of data between different modules and also handles the wireless reconfigurability. And as we mentioned before, this wireless reconfigurability will allow us to do algorithm tuning post-surgery in case we need to update the DNN. And also will actually help us add another layer of personalization as we're able to tune things per patient post-surgery depending on how things are going. So to summarize our contributions for AiEEG, we first design, train, and prune a personalized deep neural network, or in our case a convolutional neural network, for each and every single patient for seizure prediction and also localization. In addition to training a CNN, we also boost the classification performance via a novel multidimensional voting mechanism that we use, which I will get into more later why that's needed. And then finally, once we have our classifier, we then prototype it on an SoC system on chip with partial reconfiguration capabilities that is done wirelessly, and also enable it with adaptive pacing capabilities for treatment. And we can start off by talking about the prototype itself. More specifically, we use the ZCU102 evaluation board to house AiEEG, and it uses a Zinc UltraScale Plus SoC system on chip. And SoC basically just means it has an FPGA and a CPU. The FPGA deals with the TX chain and the deep learning processing, and the CPU is what handles the reconfiguration and also the flow control between different modules. But obviously the commercial device won't be this big in reality. The FPGA actually on the evaluation board can be fabricated to as small as 31 by 31 millimeters, which is way smaller than other FDA-approved implantable devices. Furthermore, to simulate our communication channel, which in our case is the human brain and the human skull and skin, we use pig meat or porcine meat. And this is actually the closest in terms of properties to actual human tissue. And this is our medium between AiEEG and actually the gateway, which would be outside the body. So in order to ensure proper function of AiEEG, there are certain real-time constraints and considerations that need to be taken into account. Specifically, we've identified 4 conditions that must be met in order for data to flow correctly through, let's say, starting from the EEG sensor all the way to the TX to transmit the classification outward. And all of these 4 conditions essentially just ensure that there's no overflow of any buffers or any memory. These 4 conditions are that the transmission rate needs to be larger than the application rate, the rate of CNN classification needs to be less than the transmission rate, but larger than the rate of ADC conversion, and finally the FIFO that we have between the classifier, the convolutional neural network, and the transmitter must be at least the size of one transmission packet in order not to cause any kind of overflow. But in addition to transmitting data outward, classifications outward, AiEEG also accepts data as well. It receives data, mostly in the form of reconfiguration files to be able to wirelessly reconfigure the FPGA portion of the SoC. This is known as partial reconfiguration, where essentially the FPGA has a static logic region, as seen right here, and a reconfigurable region, as seen right here. And the idea is that we wirelessly send a partial bitstream file to the transmitter, which then the CPU handles and uses to reconfigure only part of the FPGA, the reconfigurable region, while leaving the static region completely untouched. This partial bitstream file is actually also stored in the memory. And this whole process takes about 10 seconds end to end from transmission to reconfiguration, which isn't really a long time when considering that patients generally have seizures hours apart. So 10 seconds is basically uninterrupted in the process of AiEEG. The actual convolutional neural network that's stored in the reconfigurable part of the FPGA follows a reduced VGG16 style structure. The reason it follows this structure is because VGG16, unlike other contemporary convolutional neural networks used for image processing, it doesn't contain any residual connections. And residual connections means more weights, which will require more memory, and will also require longer to compute a forward pass. And again, we have real-time considerations to take into account. The actual input that's fed into the convolutional neural network is a one-dimensional array. More specifically, it is a single data. It is data from a single channel for a single point in time. So what we do is we first take a multi-channel, in this case N channel, intracranial EEG matrix of size 60 minutes here in this case. We downsample that to 256 hertz. So regardless of the patient's sampling rate, the network will always see the same sampling rate. Then we take this downsampled 60-minute multi-channel matrix and we break it up into smaller 4-second samples, and then take each 4-second sample and break them up into individual channels. This way, so that if a patient, as different patients have variable number of EEG electrodes that they might have, which will mean varying number of channels, the network will be able to be fed data from all of them, regardless of the number of channels. So the way the AiEEG, the way the CNN would run through the data is it would first classify this 4-second sample from channel 1 in the red box. Then it would move on to the second channel, then would do on all N channels, and once it classifies all N channels, only then will it move on to the next set of N in the next 4 seconds. And it seems like this would take a long time to run through, right? Because you would need to first do N classifications before getting a sense of what's happening in this 4 second period. But we'll see that the FPGA is really fast and the latency becomes negligible. The output of the CNN itself is actually the value of two classes, pre-seizure or non-seizure. We don't actually classify the seizure itself because seizure detection is a different field, and it actually can be done with very deterministic methods and does not require the complexity of deep learning. We're more focused with predicting seizures long before they happen. So each patient is trained on their own CNN. We keep things personalized in this way because we've tried to actually train a neural network on all the patient's data, but when we tested this neural network on individual patients, we actually saw reduced performance, and which further pushes the point of the need for personalization in our experience. Once training the neural network, we also need to take latency into account. So training this neural network is actually not enough. We actually have to prune it further, which I will get into the next slide, to reduce the computation time. So pruning the network involves removing the least effective weights or filters, depending on the way you're pruning, that affect the output of the convolutional neural network. The reason we do this is to increase the computational efficiency and reduce the time it takes to do a forward pass. For us, this was necessary because the network you saw in the previous slide was still too large for the FPGA and took too long. So we had to further prune it. The form of pruning that we've done is by pruning whole filters, which can be seen with this picture on the right here, where you have this original network, and then after pruning, these entire filters are removed and their corresponding feature maps in red. The reason we prune this way is because the resulting network after pruning just looks like any other convolutional neural network. It doesn't have any unique connections, so it doesn't require a sparse library, which would be a lot harder to implement in hardware. The actual filters that we decided to prune are the bottom 10% in terms of L1 norm. These are the filters that have the least effect on the gradient or on the output. So they're less likely to affect the classification performance. And we do this for 15 rounds. So for the first round, we'll prune the bottom 10%, then the second round, we'll prune the bottom 10%, and so on and so forth. And after each round, we also train the network for 15 epochs so it can get used to this new structure. The reason we only do this for 15 rounds is because we saw significant performance degradation after 15 rounds. So in addition to improving computational efficiency and processing latency, we also found it necessary to improve our classification performance or prediction boosting with a form of multidimensional voting. The reason for this is because some patients responded differently to the convolutional neural network as opposed to other patients. Some patients' performances were still fairly low. So we felt that a form of boosting was necessary. More specifically, we do this multidimensional voting. And what it entails is a vote in space and in time. So the vote in space involves taking a vote across all the different channels within a single 4-second time period, and then taking a majority vote of that. In addition, a vote in time is done for one single channel across multiple 4-second time samples. By doing this, we're able to actually increase the validity of our classification, regardless of the performance of the CNN for one single individual channel at a single point in time. It is worthy of note to mention that the time vote can be further personalized for individual patients, as this time window can be made bigger or smaller depending on the patient's need. But the channel vote is static because the number of channels a patient has is static itself. The voting itself is done at the gateway, not at the implant. So from this previous picture of AiEEG, it's done outside the body, essentially is what that means. The reason for this is that we're able to localize the seizure, meaning that as AiEEG inside the body classifies all of these individual channels, it will send out a single bit to represent the status of that channel, and the gateway will have this full picture of what's happening and then can make the vote as necessary. So now we will briefly go over the data set that we've used to train AiEEG. AiEEG was trained using the dataset from the European Epilepsy Database. This is the largest and most extensive data set specifically for intracranial EEG data. It does have data from other sensors such as EEG, ECG, and EMG, but it is the largest for intracranial EEG. More specifically, it had 30 patients worth of intracranial EEG data with hundreds of gigabytes per patient. So for these 30 patients, we trained 30 convolutional neural networks that were each pruned, and here is the results that we were able to achieve. Starting off with the performance of our actual seizure predictor, our classifier, here we plot the area under the curve, the AUC, for each patient, where each bar represents the AUC value for each patient's fully pruned network with and without voting. And we can see that with the addition of voting, the classification performance is greatly improved, bringing our average AUC per patient from 0.82 to 0.97. In addition, we also plot the sensitivity for the seizure horizon, which basically just means the hour before the seizure, leading up to the seizure, as a function of time. And we can see that we have fairly consistent sensitivity as time well before the seizure. In our case, this is an hour before the seizure, meaning we can make predictions up to an hour in advance. And finally, here we plot for each patient the time in warning percentage, which is basically just a measure of the number of false positives per hour that a patient has. Ideally, your time in warning should be 0. And we can see that although some patients experience really high time in warning, over half of our patients have 0 time in warning or 0 false positives per hour. Next, we will discuss the latency of our system. And here on the right, we've actually plotted the latency for doing a single channel vote for each patient. And as we've said before, to do a single channel vote, this is the time it takes for the classifier to run through all N channels, which will vary linearly depending on the number of EEG channels that a patient has. And to do a single channel classification takes about 26 milliseconds for the FPGA to complete. And at the most, for the patient with the largest number of EEG channels, this takes about 3 seconds. And this is negligible when predicting up to an hour in advance. 3 seconds is no time at all. And it is still actually faster than if we were to compute without the FPGA using something like, let's say, the cloud. So we actually compare our FPGA's performance to a cloud-based method, meaning how would the system perform if instead of doing the deep learning classification at the edge on the FPGA, we instead transmit the raw AiEEG signals outside the body to the cloud to do the classification. And disregarding the privacy implications of doing such a form of prediction and classification, the cloud-based method still takes a longer time and requires more energy, as seen on this picture on the bottom here. So here we plot the end-to-end latency of doing the classification on the edge as opposed to on the cloud, and we see that the cloud is bottlenecked by the long transmission times of sending the raw intracranial EEG data through a intra-body method such as ultrasonic communication, and furthermore takes a lot more energy because of this same reason. This is further reinforced with this picture on the bottom here, which plots the battery duration as a function of duty cycle, where a duty cycle is the fraction of time it'll take for the CNN to execute. And we can see that AiEEG has a lot longer battery duration and improves the battery performance by 4.2 times. So to conclude, we have shown you AiEEG, an embedded ultrasonically networked platform with in vivo deep learning capabilities for seizure prediction. We've shown that AiEEG is able to boost the prediction performance by up to 3.5 times through our multidimensional voting scheme. We've shown that we can achieve latency 7.8 times less and 4.2 times less energy consumption than cloud-based methods. And finally, we were able to wirelessly reconfigure AiEEG to allow for non-invasive upkeep and personalization, taking less than 10 seconds end to end. Thanks for listening. Any questions?